Okay, so discussion 17, problem 44. We're given that a rocket is traveling up, and so this thing is going up in the z-hat direction. And that's where all of its momentum is. Nothing is really happening in the xy plane here. And then something is going to happen. It's going to go and explode. So it travels up, and then it explodes into 3 pieces. Okay, so now it has stopped moving altogether, we'll say, in the z-plane, right? So, and it's only traveling in the x and y directions. This is xy. So anyway, to better demonstrate that, I have a diagram down here. So it's traveling up, so that would be towards the screen, right? And then it explodes, and it's only traveling in the x and y directions. We're asked to rank the size of the masses from largest to smallest. So as far as the xy plane is concerned, we have, let's do this. We have initial momentum is 0 because it's only traveling in the z-hat direction. So in the x direction it's 0, and then we have the momentum for B, particle B, is going to be, it looks exactly the same in the diagram. My diagram is not as good as the one on the book, but it's something like this. Okay, so that means that we have some equivalence here, right? And this is all x direction. So if we're talking about, initially we have a constant momentum, and this explosion happens, we're going to assume that it has a change in momentum equally in all directions. Okay, so it's going to, the change in momentum is going to be an equal amount for each particle. So then, in order for that to be the case, we know, so from the diagram we know that this velocity is larger than this velocity, right? So in order for this, excuse me, what I mean to say is B velocity is larger than C velocity. So in order for this to be greater than this one, that means that this mass has to be higher than this one in order to conserve momentum. So that means that mass C is greater than mass B. Okay? And then using the same logic, we could draw this out again in the y direction. I mean, we have 0 for initial, and then we have momentum for the particle A, and then it's going downwards, right? So those are negative MBVB. I mean, this is a lot less clear, but I'd say, so that means that MAVA is equal to MBVB plus MCVC. And so again, this velocity here is lower. This one is greater, and this one is also greater. And so what I mean is these velocities are greater than this one, right? And so in order for that to be the case, that means that this mass has to be higher, and these masses then a little lower than A. So that's one way of looking at it. I mean, it's sort of hand-wavy to do it this way. I'm not getting into gritty details, but I mean, just generally looking at the diagram and assuming that the change in momentum is equal in all directions, then this velocity is smaller, so that means the mass has to be greater. This velocity is smaller than this one, so this mass has to be greater than this one. So what that means then, what that implies is that MA is greater than MC is greater than MB. That's how I would rank those. Okay, so for the next problem 45, it's the same setup, same rocket setup, but now this time we're given some values and we're asked to find the velocity of piece C. So let's write down what we're given. MA is equal to 1, we'll call it 0.1 kilograms. MB is equal to 0.02 kilograms. And MC is equal to 0.03 kilograms. Okay, then we know that VA is equal to 1.5 meters per second. VB is equal to 7 meters per second. And let's pull this over here. Well, we'll just write it down here. Velocity, or the angle of B is 30 degrees below the x-axis. Okay, and now we have to find velocity for C. Okay, so we're just going to use conservation of momentum. Remember that the momentum was 0 before the explosion in the xy plane, and then it explodes, and we can use x and y directions to find. So in the y direction, it was 0 initially, and then it is 0.1 kilograms. This is for particle A times. So this is going to be mv times 1.5 meters per second. Okay, and then we have, let's call it, it's going to be in the negative y hat direction, so we'll just go negative right away. 0.02 kilograms times 7 meters per second, and then that's going to be sine of the angle, 30 degrees. And this is all in the y hat direction. Okay. Let's just set up the momentum in the x direction as well, so that we just have everything ready right away. Again, it was 0 initially, and then the next, and then also A is going to be 0 in the x direction, remember, because it's only pointing up in the y axis. So now we just plug in for B and C. So we have 0.02 kilograms times 7 meters per second, and this is, we're talking about the x direction. So B is going in the negative x direction. It's 30 degrees below the horizontal, so it's going to be cosine 30 negative x hat. So that was cosine 30 degrees x hat, right? And this is negative here. So, okay, we have that, and then it's going to be, we know the mass of C, so it's 0.03 kilograms, times the velocity of C times cosine of whatever angle is there. So I forgot to write down C for the y direction too. So, so this is true for the x direction, but also for the y direction, we do have plus 0.03 times, we'll call it, we're looking for the velocity, right? So there's that in the y direction. Have to include that, okay? And then we solve for VC. Okay, so what we can actually do is just look for the magnitude of VC in each direction, and then we can break it out into component form and find the angle. So here's what we'll do. So this is solving for the y direction. So I have tried it both ways. It works the same both ways. So you can do either one. And so this is y hat. Anyway, we know that this is in the negative y hat direction, so we're going to maintain that. And then so for the other one in the x direction, we get VC is equal to, I guess, not magnitude here, we'll do this. Trying to make it a little more clear. Right. Okay, so this is going to equal 0.02 times 7 times cosine 30, the square root of 3 times over 2 times 0.14 is 0.07. And then we divide all that by 0.03. It gives us a value of 4.04 meters per second in the x hat direction. Okay, so here are the velocities, right? Negative 2.6 in the y direction and 4.4 in the x direction. And if we just look at the diagram, I mean, I tried to emulate the diagram as best I could from the book. This roughly was about the same angle. Mine's not nearly as good, but if you look at the Book's diagram, it makes sense to say that this is larger than this. Okay, and so now total velocity is equal to 4.04 meters per second x hat minus 2.6 meters per second y hat, and we can find the angle as well. Angle is going to equal the arctangent of y over x, negative 2.6 over 4.04. And this gives us a value, it comes out to 32.7 degrees. I would chalk it up to rounding error. I would say that this is probably about 30 degrees. Right. Okay, and the magnitude. And if you're asked to find something like this and give the exact value, then I would plug in the exact value. But a lot of times you're asked to give an estimate. And then we find the magnitude. And that gives you about 4.8. So the magnitude of V is about 4.8. Okay. So again, I used conservation of momentum in the y direction and in the x direction to solve for the velocities in those respective directions, right? And so we have VCY, and I solved there, VCX, I solved there, and then that gives you your vector. If you have questions about this, please let me know. Next problem. Page 326, problem 22. Okay, so we're given a scenario where we have a block sitting at the end of a table, and then we place a ball at the end of a spring that's right next to the block. Right, this is the initial position, and then we compress this spring back here, a value of x naught, and then we let that spring go. The ball goes flying, knocks into the block, and both the ball and the block sail down off the table and land some distance away from the table. So we are asked to find what is this distance that it travels here. So considering that these things, these block and ball actually stick together in the collision, this is inelastic. We'll use kinematics at the end to find d. We'll be able to use conservation of momentum for the inelastic collision, because momentum will be conserved in this case, but the energy will not. And then so up here in this situation, we'll be able to use conservation of energy. So let's get started. So here we're going to have, so this is the initial setup, but we're going to say that let's just start at this. This isn't really going to do us any good. Let's just start here. So we'll say we've pulled the spring back half kx squared, right? We'll call it x naught squared. That's the distance. And this is going to equal, we're just considering the energy for the ball right now. So this is going to equal, and the final energy of the ball is going to be, and the ball and spring is going to be half mv naught squared. Okay, which means since we're going to need a velocity for the inelastic collision, we're going to solve for that. So that gives you 2's go away, and then you get k over m square root of x naught. Okay, so using conservation of energy for the ball before it strikes the block, right? Because we're going to use the ball striking the block in the next part. So we've just started here. We have spring energy, spring potential. So this is spring potential, and then we have kinetic energy of the ball. Okay, so plugging those in, we solve for V, no problem. And then so next we have down here. Let's highlight this so that I can find it later. Okay, so next we're going to say that the m ball, v ball, plus the initial momentum of the block is 0. So these things added together. So now I'm considering when this ball is traveling, right? So this has a velocity v. This is the velocity. Okay. This thing strikes into the block, and then so now they're both going to stick together and travel. They're going to travel this way. Okay, so that means that there's a net. This is m plus little m. So that's the total mass of the two things together. And then we have another velocity here. We'll call this vc for now. Okay, so now we solve for this one. So vc is going to equal mb, mass of the ball. By the way, that's this one as well. So mass of the ball times k over mass of the ball times x naught. Right? That's the velocity of the ball. Okay, and then we have 1 over m plus m mass of the ball. Right? Let's just rewrite that down here so that we have so we can find that later as well. So now we have, okay, this over this is going to give you square root mass of the ball times k x naught all over mass of the block times mass of the ball. Okay, now we need to consider some of the properties of what is happening before we start on our kinematics. So this height, this initial height here, this is going to be y naught, this is going to be h, right? We want our final height to be 0. The initial launch angle is 0 degrees because this is just flying horizontally off the table. So there is no angle here. So if we look at the y direction, we have y naught plus v naught y times t plus half at squared. So remember, final height is 0. This is h. This is going to be v naught y is equal to v naught sine theta. But our launch angle is 0. So this is sine 0, which is 0. So this is 0. So there is no initial y velocity. There is an initial x velocity. But right now we're looking at the y equation. Okay, and we can find our time from this. So this goes to 0. This goes to 0. Now we're left with this, h minus half g t squared, because our acceleration is negative g, right? Okay, and so now we want to know how much time is this thing going to be in the air as it's flying down off the table. So solve for time. T is equal to 2h over g square root of. Okay, let's highlight this as well to keep track of that, because we probably will need this in a moment. So now let's look at the x direction. So now the launch angle is still 0 degrees. We know a time. Now we have an expression for time, so we might be able to figure this out. So let's see. What is our x is equal to x naught plus v naught x times t, right? Where v naught x is equal to v naught, what would we call this? Cosine theta. So in these, I just want to point this out real quick. In these small asides that I'm doing, v naught is in fact, this is going to be your vc, right? The launch velocity is vc. So when I'm writing these out, these are just the general expressions from our kinematics. So the subscripts here don't really necessarily indicate what's really going on. I'm just showing you the relationships. Okay, but now in this, since this is vc, so now we have x is equal to 0. Our initial launch distance is 0, right? So if we look at this again, let's just start here. Let's call this 0. We want to know how far it goes. So that seems reasonable. So x is 0 plus vc, right? Cosine of the angle is 0, which is just 1, times time, and we just found an expression for time here. So let's multiply that in. So that's going to be 2h over g square root of, right? So that means that x, the distance, is equal to, now let's go find vc. Here it is. Okay, so it's x naught over the total mass, it's the mass of the block plus the mass of the ball, times square root of the mass of the ball times k. And then, so this is just 1, and then we have square root of 2h over g. So now let's call this distance is equal to, if we just wanted to simplify a little bit, we'd have x naught over m plus mass of the ball times 2h mass of the ball k over g. So that's your distance. Next problem. Okay, so we are given this setup where we have a ball with an initial velocity flying at a block that's tethered to a pole on a table, right? So this thing is flying straight. It's going to collide with this, and this block now, because it's tied to this pole, is going to do circles. Okay, so we want to know what is the tension force, right? Okay, so first step, we need to solve for we need to solve for the conservation of momentum. Okay, we're given an initial mass for the ball and a velocity for the ball. So let's figure out what is the momentum there. So we have 2.45 kilograms and 13.5 meters per second. Okay, that is going to equal the final momentum. By the way, this is also another inelastic collision where this ball sticks to the block, right? So that's going to be the total mass, which is going to be m1 plus m2, which we have these values, they're given, and that times final velocity, right? Okay, so the initial velocity of the block is 0. This velocity flies in here, sticks together, and then goes. All right, so VF is equal to 2.45, 13.5. This is kilograms meters per second because we're in momentum. Now this is divided by kilograms. So it's going to be 2.45 plus 0.45. That's going to equal 11.405 meters per second. So that's useful. So all I did was just use conservation of momentum. This hits this and sticks together, right? Next part. So now the next part's a little trickier, but it's still rather straightforward. So what's going to happen is, again, these stick together, and this now has some velocity. So these two masses are added together. There's some velocity where this is tethered to the pole, so it's going to spin in a circle. So now the only force acting on forces acting on the block and the ball together are going to be the tension force, and because it's spinning in a circle, we have the net force is the acceleration. It's the acceleration force, which we call centripetal force, right? So it's going to be mv squared over r. Okay, and so the velocity we know we just found. This is going to be the velocity. We know what the mass is going to be. It's the total mass. It's this. And then r, we're given is 0.3 meters. So all we do is plug this in. So the tension force is equal to 2.45 plus 0.45. Does that look like 5? And then 11.405 squared. And then times 1 over 0.3. And that's going to give us a value of 1,257.38 newtons. So that's how you solve that problem. Okay. So I've gone through that one rather quickly because we're already 20 minutes into the lecture, and the next two problems are actually quite a bit of work. So I'm going to try to get through them as quickly and concisely as possible. Okay, we're given two objects. This is number 39. I don't know what page, 327. So we have object 1 traveling along this direction, 8 meters per second, x hat. we have another object, object 2, traveling in this direction, 10 meters per second, x hat, right? We're given masses. Mass 1 is equal to 5.15 kilograms, and mass 2 is equal to 6.25 kilograms. And what we're asked to determine is the final velocity for each ball. Okay, so since the collision we're told is elastic, these things are going to collide and then bounce off each other. And in an elastic collision, elastic collisions, momentum and energy are conserved. In an inelastic collision, momentum is conserved, but there is a loss of energy. So a loss of energy to thermal energy or outside forces, and so energy is not conserved in an inelastic collision. Okay, but in this case we have this happening, so we can use this information, right? So let's set this up. Let's figure out what is the initial momentum, right? We have 5.15 kilograms times 8 meters per second plus, it's actually minus 6.25 kilograms times 10 meters per second. And that's going to equal, we have some momentum for each ball. This is final, okay? So then, using the conservation of momentum equation, this is what we end up with. Or we could just say that this is m1 v1 plus m2 v2. Okay, we know what m1 and m2 are, but we might not want to just, it's going to be easier to write m1 and m2 than it is 5.15 and 6.25 a whole bunch of times. So this is equation 1. Okay, so now let's use conservation of energy to find a second equation, because right now we have one equation and two unknowns, right? These are unknown. So now we need to figure out, so what is the total kinetic energy in the initial phase? So this is what mv, so this is kilograms 8 squared, right, plus half. And this is also going to be 6.25 times 10 squared, and this is equal to final velocities, right? So we'll call this m1 v1 squared plus half 6.25 v2 squared. Okay, so simplifying a little bit, now we have 2 times, if you just work out a little bit of the math, 2 times this is going to be in joules. Right, because we have kilograms meters squared per second squared, which is a Newton meter, which is a joule, right? So that works out. So now we just have m1 v1 squared plus m2 v2 squared, and this is equation 2. So now, rewriting these down here, just for clarity's sake, equation 1, negative 21.3 is equal to m1 v1 plus m2 v2. Okay. Equation 2 was 954.6 joules is equal to m1 v1 squared plus m2 v2 squared. I should just note that this is actually in units of momentum. So what we have here is we have initial momentum, we have initial energy, initial kinetic energy, we know m1 and we know m2. The only things we don't know are v1 and v2, and those are the final velocities. That's what we're asked to solve for. So now you have a system of 2 equations, 1, 2, with 2 unknowns, v1, v2. Okay? I'm just going to simplify things just a little bit further. I'm going to take negative 21.3 over what was M1. Let's get rid of M1, 5.15 kilograms, okay? That's going to equal V1 plus M2 over M1, which I'm just going to designate as some other variable. Oops. M2 over M1, I'm going to call alpha, and then I'll just bring that back at the end, okay? And then equation 2, well, we have 954.6 over 5.15 kilograms. This is joules. It's kilograms meters per second. So that equals V1 squared plus M2 over M1 V2 squared. All right, I'm just kind of trying to keep these coupled so we can see what's going on here. So that means, so I've just simplified and I've rewritten the equations. Now I think these are a little more simple looking, and it should be just easier to work with in general. And so I've saved this value alpha here. And again, this is just simplifying. This is what we started with, okay? So we used conservation of momentum to find our first equation here. Then we used conservation of energy. This was our conservation of momentum here, and then conservation of energy here, right? So that gave us equations 1 and 2. And then I just did a little bit of simplifying so that they look easier to work with, and so that way it's easier to not get confused as you're slogging through algebra, right? And then I've turned this blue so that we can see it later, so because we're going to need that later. So now at this point we just solve. So we take V1 is equal to right, and then we plug that into the next equation. So we solve for V1 here, plug it into the next equation, just like from algebra class. V2 squared plus alpha V2 squared. So that gives us equation 1, right? And then this was equation 2, but we plugged in. So now we plugged this into this next equation. So 0.359 is equal to 4.135 squared plus alpha squared V2 squared plus alpha V2 squared. And then what was it? Negative 2 alpha V2. Right, that's going to be negative times 4.135. This will be positive because they're both negative, so that leaves us with that. Okay, so now we can solve for V2 using a quadratic equation, because we have something here. We know, because remember that alpha is actually a constant, right? So we can actually plug in all of these numbers and solve for V2. So let's figure out what V2 is. This way. We need V2 squared times that, right, plus 2 alpha times 4.135 V2, and then we have plus 4.135 squared minus 185.359 is equal to 0. So now we have some sort of quadratic form that may be a little more familiar, right? So I'm just going to do this. This is some constant here, so we don't really need to worry about too much. We take over both of these, we're going to use alpha squared plus alpha. That equals 0. So now look at this. Now we have what we need squared plus some constant times v. So it's V2 squared plus a constant times V2 plus a constant. So this is A equals 1, B equals this, and C equals that. So I'm just going to plug these into the calculator to simplify again. Okay, so I've just simplified a little bit by plugging in the values for alpha here and here and here, and then just finding the constants that are sitting as our coefficients. And remember, alpha, as earlier, I just took the ratio of the two, and alpha is 1.213. Okay, so that's just a unitless constant that I found. Okay, so now I'm going to take V2 is equal to, so this is just your standard quadratic formula. Four times C, which is negative 62.68. Okay, and then I should come out with two values, so let's figure out what those are. Okay, so I plugged in the values for here, and I ended up with two values, positive 6.266 and negative 10.003. Okay, and let's recall what it is we're looking at here. These are velocities in the x-hat direction, right? Because we have two particles that are flying towards each other in the x-hat direction head-on. So that means they're going to fly back in the opposite direction because we're told this is elastic. So these things collide like billiard balls or something and fly backwards in the opposite direction. So right now I just found velocity for V2, which is this one. So this one is going to be traveling initially in the negative x-hat direction, and then finally in the positive x-hat direction. Okay, so right away I'm going to say that this one telling me that this is a negative x-hat direction for V2 is wrong, because we know from the diagram it should be traveling in the positive x-hat direction. So V2 is equal to 6.26 x-hat. Okay, so now we can just plug that back into the original system and find V1. Here's the equation that I'm going to use, this one. So I just plug V2 into that, and I should come up with a value that makes sense. Yeah. Okay, not sure what happened there. All right, so then that means that this is equal to negative 4.135 minus 1.213 times, what was it? It was 6.26, and this is all in meters per second. So plug that in, and before I even do that, I can see that this is going to be a negative value, and that's good because that's what we want. We want the velocity for V1 traveling in the negative x-hat direction. Okay, so let's see. So plugging this in, I get V1 is equal to negative 11.73 meters per second in the x-hat direction. So these are the final velocities. I should note that it actually occurred to me after going through all of this, the last calculation that we did, number 39, you can do it that way, the way I did it, which is kind of fun if you're into algebra, but also you could just use what's in the book. For this type of problem, you're actually given these equations in the summary of the chapter. Pretty much exactly the same answers. So, okay, we're told that we have a laboratory experiment. Real quick, the diagram looks something like this. This is an electron, it's traveling. Here's another electron, it's sitting there. And then after the collision, we have an electron traveling this way, and then something like this. So actually the very first question is it possible for the initially stationary electron to remain at rest after the collision? Well, no. If we consider Newton's laws, right? We had something, I think this is paraphrased, but an object at rest stays at rest unless acted on by an external force, right? Unless, or until, I think it's until, acted on by external force. Or an external change in momentum, because a force is a change in momentum, right? And so you have an electron sitting there with p equals 0. Then you have another electron here carrying momentum, traveling at a velocity, right? Or we could say this is p, not 0. And then there's just no way. I mean, these things weigh about the same. they are exactly the same weight, excuse me, for mass. And so if this were supermassive, if it were like, I mean, compared to an electron, if it were supermassive, if it were like the size of a, I don't know, a person or a car or something, yeah, I mean, obviously this electron would just bounce off or just stay there. And this would remain at rest. But as it is here, if this were billiard balls or if this is anything remotely the same, this is going to take off in some direction. So no, it cannot remain stationary after the collision. Okay, part B, we're asked to find the speed of each electron after the collision. So let's write what we actually know, right? So we're told the initial velocity was, no, we're actually told that the initial kinetic energy is 50 keV. And if you do the conversion, that turns out to be, that's why this is 50.5. So if you do the conversion, this turns out to be, well, I think it was like 1 keV is equal to 1.602. This is what I have, 10 to the negative 19 joules, and then you would actually multiply this. That's for 1 EV, excuse me. So then you would multiply this is equal to all of that times 10 to the 3. So then you have half mvi squared is equal to the initial kinetic energy, 50 keV, right, is equal to 50.5 times 10 to the 3 times 1.602 times 10 to the negative 19 joules. So then you solve for this. Oh, by the way, let's move this down here. By the way, the mass of an electron is something that is known as well. That is, hang on one second, 9.109 times 10 to the negative 31 kilograms. Okay, so you can use all of this. The point of doing all of this before getting started, really, with conservation laws is that we can identify a known constant for v, the initial velocity, right? And that gives us, if we plug all of this in, if we plug these values in, including this one, and we solve for vi, then we end up with 27 times 10 to the 8 meters per second. That's how fast the electron was traveling. About a third of the speed of light. Okay, then your initial kinetic energy also is a known value, and that's 8.09 times 10 to the negative 15 joules. That's your initial kinetic energy. Okay, so now since we know that this collision is elastic, because that is exactly what we're told, also we should point out that this is 40 degrees. We're going to need that. That's given to you in the problem. I didn't solve for that or anything. So now we can use conservation of momentum and conservation of energy as usual, right? So we have m, the mass of the electron 1 times velocity 1, right? We'll call this I, is equal to mass 1 times velocity 1 final plus mass 2 velocity 2 final. Okay, we don't really need to include, if we just call this initial velocity because only the first one is moving, that's fine. That makes it a little easier to comprehend. So now also consider that the masses of the electrons are the same. So since they're equal, we can just kind of cancel these out. And now we're left with, from conservation of momentum, we have this, right? Okay, but also now we need to consider that this is a two-dimensional problem because, well, this is flying in the x-hat direction, and then this goes off with some components in the x and y, and this has components in the x and y. So what that means is that it gets a little more complicated. So we have vx so the initial velocity in the x direction is going to equal the final velocity in x, 1x plus v2x. And that is going to equal v1. What are we going to have? We're going to have cosine 40 plus v2 cosine angle 2. We don't know what this angle is yet. So that's one equation that we have. Let's just write it like this. This is equation 1. Now, we need to go to, if we look at the diagram again, this has no momentum in the y directions, only in the x direction. So that means that the initial momentum is 0. So 0 is equal to, and then we had the electron 1 is going in the y direction, so we have a positive sine 40, and then it's a negative v2 sine angle 2. So this is equation 2. Okay, and then equation 3, we are just going to use standard conservation of energy, excuse me. So this is v1 squared, vi squared, excuse me. That's going to be a known constant. This is just vi. And then this is going to equal the kinetic energies of the two after the collision, right? Well, notice that, again, these masses are all going to be equal. Those cancel. Well, these are going to cancel. So now let's do this. So equation 3 is actually equal to vi squared is equal to v1 squared plus v2 squared. So now we have 3 equations, 1, 2, 3, and 3 unknowns, right? We have 1, 2, excuse me, that's only 1. So it's 1, 2, 3, and those appear in every equation, right? 1, 2, 3, and then 1, 2. So what are the 3 unknowns that we need? Well, that's v1, v2, and the angle. So this is what we want to find out: v1, v2, and angle. Okay? These are the final velocities of the particle. All right, so now we have to solve this system of 3 equations. Just going to rewrite them real quick so we can see what's going on. This is going to be v1 sine 40 is equal to v2 sine theta 2. And then we have also vi squared is equal to v1 squared plus v2 squared. Okay, great. Okay, so then let's take this equation here and plug it into another one, because that's the easiest one to solve for right now. So let's go v1 is equal to v2 sine theta 2 over sine 40. Okay, then we'll plug that into, which one? We're going to plug that one into this guy. Let's see. Why not? So now we have vi squared is equal to, I don't know if I want to write in all pink, that's going to be sort of distracting. So we go vi squared is equal to v2 squared sine squared theta 2 over sine squared 40 plus v2 squared. That also equals v2 squared sine squared theta 2 over sine squared 40 plus 1. We could just say vi now is equal to v2 and then the square root of this. Actually, sorry, we already know what vi is. We want to know what v2 is, so then we want to solve for v2. So let's try that one again. So we go v2 is equal to, it's going to be vi. This is just going to be sine squared 40 over sine squared theta 2 plus sine squared 40. Or it equals VI sine 40. And go 1 over the square root of those two things, right? Something like that. Okay. Then we go back up to the next equation, right? So then we plugged into here, and then we'll plug this back into here, what we found. This was actually going to be V2, so we'll plug this value into this equation and see what we get. So VI is equal to V1 cos 40 plus V2 cos theta 2, right? And we just figured out what V2 is. We know what V1 is. It's in terms of V2. So now we have VI is equal to, it's going to be V1, so it's V2 sine theta 2, we have cosine 40 over sine 40 plus, what is this, squared, or, oh, cosine, oh, it's just cosine theta 2. Okay, like that, I see. And then we plug in for V2, where we have VI sine 40, 1 over, let's do it down here, 1 over sine squared theta 2 plus sine squared 40. This is square root. And then we have sine theta 2 cotangent 40 plus cosine theta 2. All right. Okay, so just before I finish this up, we are kind of running out of time. It shouldn't take too much longer. We might just go a little bit over an hour, but I was going to say you could solve this numerically. We've done a problem similar to this where you fill in a spreadsheet and try to get it to match the value. Or you could start here with our system of 3 equations. If you know of an equation solver, that would work as well. I'm just going to continue with this analytically because we're actually pretty close to the answer. So these cancel, so this is going to be 1 is equal to sine squared 40 over sine squared theta 2 plus sine squared 40, right? And this is all under square root. So I've just changed this a little bit. Sine theta 2 cotangent 40. Going to be a little sloppy, but hopefully you can follow along. And then so I take this to the other side, take this to the other side here, and that gives us square root of sine squared theta 2 over sine squared 40 plus 1, okay, is equal to sine theta 2 cotangent 40 plus cosine theta 2. And then I square both sides, right? So this is just going to give me sine squared theta 2 plus 1, sine squared 40, and this is going to equal sine squared theta 2 cotangent squared 40 plus cosine squared theta 2 plus 2 cosine theta 2 sine theta 2 cotangent 40. Okay, continuing on. Okay, so now we have 2 terms. Here's sine squared theta 2, sine squared theta 2. Let's take that to the other side and see if we can simplify. There's literally just, I think, a few more lines of this, and then we should be about done. Or, by all means, try to solve it yourself. Nothing wrong with that. Okay, we're getting somewhere. Why do I say that? Because this looks like we're stuck, right? But cotangent squared is actually going to be equal to an identity involving cosecant squared. And here we have sine 1 over sine squared. That's a cosecant squared. So now we have sine squared theta 2 times cosecant squared 40, right? And then this is going to be minus, it's going to be minus cosecant squared 40. Okay, that's going to be minus 1. And this equals all this stuff here. I'm not going to rewrite it. I'll just duplicate it. Easy enough. All right, continuing. So, okay, well, these cancel, and then you're left with 1, right? And, oh, also, there was still an extra one. See, remember, this was still here, so I needed to add this in, because what we have here is we have 1 plus sine squared theta 2. Okay, and then, so we have this cosine on the other side. We can bring that to the other side, so minus cosine squared theta 2. That's going to equal 2 cosine sine theta 2. This is actually going to come out to be a different identity as well. This will be 2 sine 2 theta, right? So, all right, or we might not even have to worry about that. Let's just continue on with what we got and see if we can get to the answer this way. Okay, good. Actually, we can recognize that 1 minus cosine squared theta is actually sine squared theta. So that's going to give us 2 sine squared theta 2. And then let's just divide out through the other side, because we can probably cancel some stuff over here, because we have 2 sine theta 2 cosine theta 2. And that's going to leave us with cotangent of 40. Right? So we're very close to getting the answer here. These cancel, that cancels, that cancels. So now we have tangent theta 2 is equal to cotangent 40, which means that the angle theta 2 is going to equal the inverse tangent of, now we just do this, cotangent 40. Because cotangent 40 will give you a numerical value. So we plug that into a calculator, and let's see what we get. And I plug that in and I get 50 degrees. So that is the angle theta 2. So that actually will allow me to plug in and solve for the other two velocities. Okay. So now we can just use two of our original equations with two unknowns, and we got VI is equal to, well, let's go with the first one first, actually. So we have V1 is equal to V2 sine 50 over sine 40. Let's just do the calculations at the very end, right? So that's going to go, then now we have VI. So now we have VI is equal to V2, right? Sine 50, sine 40. Well, we can just do cotangent 40. Cotangent 40 plus cosine 50. So then V2 is equal to VI over all of that. Okay, recalling that VI is equal to 1.33 e to the 8 meters per second. You plug all of this in, and then you end up with a value of V2 is equal to 8.549 times 10 to the 7 meters per second. Okay, then we plug that into V1. Plug all that in, and then I get V1 is equal to 1.019 times 10 to the 8 meters per second. So these are the values I found by solving it analytically. I would be interested to know if anyone solves it using some sort of system of equation solver, if you get the same answers. All right. Thanks.